All right, this is part 2, Unit 11C. We're looking at proportions and the golden ratio. Next, we're talking about the golden ratio and some of its applications. In nature, we're not going to give you a whole lot of that, although you can find it in your textbook. If you look up something called Nature by Numbers, it was put together by a gentleman from Spain. It's quite impressive. That shows where you can find this golden ratio naturally occurring in the environment. It's pretty unique. So again, I'll leave a lot of those examples. If you are curious to look into those, you can. But here's an intriguing connection between the golden ratio and nature. It comes from a problem in population and biology, and it was first posed by a guy the last name of Fibonacci in 1202, that year, 1202. So his problem essentially asks the following question about the reproduction of rabbits. And it's a little wordy, so I've got a little picture down here. Your text has a little picture that will hopefully help you out. So suppose that a pair of rabbits takes 1 month to mature into adults. So here's your first pair of rabbits on the first month. Takes them a month to mature. Then produces a new pair of babies the following month, and each subsequent month. So they start as a pair as a baby, then it takes them 1 month to mature. So we go from one pair and we still have another pair. So one pair, and then that one pair matures. So there's still one pair. And then, let's see, and it says, so then further we suppose that each newly born pair of rabbits matures and gives birth to additional pairs with the same pattern. If no rabbits die, how many pairs of rabbits are there in the population at the beginning of each month? And so it's, well, I'll just kind of leave the text there, but it's, well, then you can't see the bottom, so I'll scoot it down like this. But it's kind of interesting. So, our first month we have one pair. Our second month we have still the one pair, but now they've matured. So when we go into our third month, this pair is going to give birth to a pair, but then they obviously remain. So there are now two pairs. Then when we go over to the next month, so I guess I'll just write this is month 1, month 2, month 3, 4, 5, and 6. Okay, so we go to month 4. This pair continues on. This pair matures, but this pair also, I should have said, gives birth again to a pair of rabbits. So we're up to 3. Then we'll start bottom to top here. This pair matures. This pair has another pair, and then they move on. This pair had matured, so they move on, and they have another pair. So now we're up to 5 pairs on month 5. And then on month 6, going from top to bottom, this pair matures to adults. This pair is an adult, so they have another pair, and then they move on themselves. This pair is an adult, so they move on, and they have a pair. These are young, so they turn to adults. These are adults, so they move on, and they have another pair. And if you count all those up, you get 8. So you get this pattern of 1, 1, 2, 3, 5, 8. And it continues on. And notice that here, if I take 1 plus 1, I get 2. If I get 1 plus 2, I get 3. 2 plus 3, I get 5. 3 plus 5, I get 8. 5 plus 8, I get 13. 8 plus 13, I get 21. And so on and so forth. And so the Fibonacci sequence is what this is called. Turns out to have a lot of unique properties. And again, it's found by just taking the previous 2, adding them together, and then you get the next one. So again, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so forth. So there are populations. So the way you write this sequence is you have to define, the first 2 months, F1 and F2. So that's the first number in the sequence, the second number in the sequence, they're both 1. And then from there on out, we get this pattern right here, that if I want to go basically to the next term, it equals the sum of the two previous terms. So when it says f of n plus 1 equals f of n plus f of n minus 1, this is like 2 before, this is 1 before, and this is kind of now, or the one you're currently on. So the one you're currently on is just the one right before it and the second before that, and the sum of all those together. So again, that's just 1 plus 1 equals 2. And then the next one is 1 plus 2 equals 3. And 2 plus 3 equals 5, and so forth. That's how that formula generates. Now there's a connection between the Fibonacci numbers and the golden ratio, and it becomes pretty clear when you compute the ratios of successive numbers. And as you get these ratios, as you take these ratios, they get closer and closer to the golden ratio. It's quite a unique setup here. So you know, if you start with the third and second term, that ratio 2 over 1 is 2. Then the fourth and the third, which is 3 and 2, that ratio is 1 over 5, or 1.5. Then the next one is 1.667, then 1.60, then 1.625, 1.615, 1.61905, and so forth. And notice that it really begins to hone in on the golden ratio as you get further and further on in the sequence. It's just a kind of very interesting thing that came about from a pretty intense question that Fibonacci asked. And this, if you look up Fibonacci numbers, you will find videos upon videos upon videos of people who have dedicated their lives or dedicate research facilities just towards looking at this sequence. Okay, now last thing we're going to talk about is another sequence called the Lucas sequence. It's closely related to the Fibonacci sequence, and it begins with the number, so L1 is 1, L2 is 3, so it starts out, it goes 1, 3, then it uses the same way, the same kind of pattern as the Fibonacci sequence. So you do 1 and 3 are what you start with, then 1 plus 3 is 4, 3 plus 4 is 7, 4 plus 7 is 11, then 7 plus 18 is, excuse me, 7 plus 11 is 18, then 29, then 47, then 76, then 123, and it keeps going. There's our first 10 terms of the Lucas sequence. And if you start dividing these out, so if you take 3 over 1, that's 3, then 4 over 3, that's 1.33, and then 7 over 4 is 1.75, and then 11 over 7 is 1.57. And if you continue this on down, this will eventually approach a single number. And the question for you that you'll answer in your homework is, what number does this approach? And again, this is just a different sequence that we're looking at called the Lucas sequence. And it's kind of fun to play around with there. But that wraps up this portion for 11C. If you have any questions on the Fibonacci sequence, the Lucas sequence, the golden ratio, please do not hesitate to let me know. And if you have a moment, take a look at and just Google Nature by Numbers. And the guy's first name is Cristobal. And it's pretty interesting to see how this golden ratio appears in nature.